Very simply, you have your waveform diagrams, you have your voltage reference, you have your lagging current. For most power factors, they would have a power factor around about 0.7, so it'll give you about 45 degrees. And what we're going to be doing is to push the current, which is this blue line. We're going to push this current back closer to the voltage reference. When we do that, we end up with a basic diagram that shows the electrical circuit. We have a utility feeding current into the system, and the system is comprised of resistance, X sub L, X sub C, which is inductance and capacitance. And between them, this part is kVARs, this part is your kW. So we have vectors that show the resistance, vectors that show the effect of the inductance, and a vector showing the effect of the capacitance. When we sum these vectors, the verticals, over into kVARs, we have a power factor triangle. And the bottom we've got kW still. Here's the resultant, the kVARs. And on the long side we have kVA. This angle is your power factor angle. We're going to shrink the kVAR, and they'll give us a new power factor. If we have the short kVAR and the long kVAR, we can now tell you the change in your line currents with this formula. Basically, less amps means save power. So an old rule of thumb is if you have a perfect power factor, say 1.0 minus your existing power factor, this is your savings. For example, if you have 1.0 minus 0.7, your existing power factor, you have 0.3 resultant. Very simply, 30% savings.